Hey guys, this is our Friday lecture. I think it's lecture 5. Thank you for dealing with all the testing stuff. I just so miss my classroom. I miss my classroom. I miss being able to test my students in my classroom, to be able to give the exams I want to give. I know it's not perfect. Little is perfect right now, but we're going to adjust. We're going to adapt. We'll take a look at things. It'll be a while before I even have a chance to even look at what you've done. So, but I thank you for dealing with it all, and we'll adjust. WebAssign will get easier. There's some nuances to it. That's very particular about parentheses and very particular about units. But it is what it is. I mean, we'll make it work. So I want a little reminder of what we've been doing since everything was kind of focused on the test. We were in chapter 4, which was not on the test, okay? And what we're trying to do is we're trying to talk about, maybe you should stand up. Stretch, just catch your breath. Maybe you should pause the video. You've written down this, okay? You haven't written down these two things, and this is your homework. Oh, and this is 4.4. Sorry, that's 4.4. This is your homework. What I really want you working on over the weekend. Okay, so that's homework from 4.4. So just pause the video. This you already have in your notes, but these two things you don't have in your notes. So just pause it and write that down. Okay, it's the extreme value theorem and a major result from calculus. So I'll just give you a moment and let you do that. Okay. Now that you've done that, I guess maybe it took longer than a minute. Sorry. Our homework in 4.4 is the first couple ones aren't so long. They're just graphing problems. Okay. You're just looking not where you graph. I know you're like, Dr. Warren, you've never made us do that. No, you're looking at graphs and you're trying to identify certain things. Okay, these next ones you're kind of doing like some of the stuff that we're going to do in the beginning, and the last 3 are your favorite types of problems, which are your application problems. Okay, there's harder application problems in the next section that we'll get to later on if we get a chance to come back to chapter 4. Okay, but I want to remind you what it means because Section 4.4 is all about global maxes and global mins. That's what it's about, global maxes and global mins. And I want to remind you what it means to be global max, okay? Because these can show up on questions on the test. F of C is a global max. Now your book uses absolute max, okay? But I'll use global max. F of C is a global max of f on the closed interval AB if it's the biggest. Like if f of C is the biggest that f of x can get for all x's in the closed interval AB. So it is the biggest. It is the Usain Bolt. You're like, who's Usain Bolt? He was the dominant sprinter, okay, for a decade. Okay, the dominant sprinter in the world for a decade. Okay, this is the largest guy on the interval A to B. Okay, this theorem takes about 2 days in Math 410, okay, which is one of the hardest math classes that we offer at JMU, and it takes about 2 days to prove in there. Okay, so what I want to do is we're definitely not proving it, but I do want to state it for you. It says if f is continuous. So once again, continuities are BFF. Okay, if f is continuous on the closed interval AB, then there exists C and D that are elements of the closed interval AB such that f of C is less than or equal to f of x, which is less than or equal to f of D, okay, for all x that are in the closed interval AB. So what the extreme value theorem is doing, it's guaranteeing that there is a global min and there is a global max on your closed interval AB. And you guys can try this. So at your seats, I'm just going to mark something. Let's call this 2. and this 7. So that's kind of like my closed interval that we've got there. And now all I want you guys to do is draw a continuous function. So you've got this, you draw a continuous function f, okay, at your seats. You draw a continuous function f on the closed interval 2 to 7. You're like, Dr. Warren, I don't remember what continuous is. You do, okay? Draw a continuous function. Okay, now what I'm going to try to show you is that there are these extreme values. There are these extreme values related to the graph of your function. So I'll draw one here. Okay, I'll draw one. Maybe mine goes something like this, goes down, and then it swings up like that. Okay, so there's my f. Super continuous, super smooth. Okay, it's no corner points, so it's actually got a derivative. Okay, but I want to guarantee that there exists these guys down here where the range value f of c is the min, and the range value f of d down here in the domain is the max. Okay, so I'm going to just draw this here. So I'm asking what value, as I move from along this slider between 2 and 7, when is the function the smallest in the range? And you're like, well, Dr. Warren, is it here? And the answer is no, because there's another point right here. And this value right here is my f of c. That value is my f of c. The graph will never dip beneath this value as far as its range is concerned. Now d actually occurs all the way over here at 7, at this endpoint 7. And this is my f of d. Okay, so now what I want you guys to do on your graph is I want you to find your c and your d down in your domain and mark your f of c and mark your f of d. And this is where I would love to say cheat off each other, look off each other, but you can't do that right now. So all you can do is cheat off of me. Okay, and now pick any other x. Pick any other x in the closed interval 2 to 7. Any other x. So I'll pick an x here. Notice f of x is less than or equal to. F of x falls between f of c and f of d. Pick an x over here. F of x falls between f of c and f of d. Okay, so this is not a proof. This is just merely a graph showing you what the extreme value theorem is saying. Okay, so if you have continuity on a closed interval, you've got a global max and a global min. Okay, so if your mathematical model for whatever discipline you're studying this course for, okay, is continuous on some interval that they're interested in, some closed interval, then you know it has to have a max and it has to have a min. Okay, once again, continuity is your BFF. Okay. Now, finding that global max and global min, that's a different question. Knowing they exist, that's the extreme value theorem. Finding them is a lot of work, especially if you don't have calculus. Okay? Because there's infinitely many values. Say that. Say that right now. Okay, you're already zoning. You're already zoning. Here, let me just, we need something. We haven't done this in a while. Let's just, let's get up. Come on, let's get up. Come on, let's, I know I'm clapping off key. All right. See, if you don't pay attention, it's going to happen again. It's going to happen again. Right. Don't make me go dead. Okay. Major theorem. Major theorem. If f is continuous on the closed interval AB, then we know it's got to have extreme values. It's got to have a global max and a global min. This theorem says the global max must be either a local max or one of the two endpoints. It's got to occur at f of a or f of b. Okay, it's got to be either f of a or f of b. So if you're going to be hunting for global maximums, okay, this theorem says all you got to do is look at the local maxes and look at the two endpoints. Pick the biggest of those guys. Put those guys in the octagon, see who wins, okay? And the biggest guy standing is your global max. Now this is a lot different. There's infinitely many values. There is infinitely many values between A and B, but there's usually just a small number of local maxes in our problems, okay? And we have our two endpoints, and then we're just trying to find out when is the function the largest amongst those. And so this drastically changes things. So this is a major theorem for this course, okay? So it says that a global max must occur at a local max or one of the two endpoints. There's an equivalent theorem that says a global min must occur at a local min or the two endpoints. Now I'll just draw a couple of ones that will show you this. Like for example, let me just make this A, this B. This would be a continuous function where the global min is f of b, but the global max is f of a, and so both the global max and global min occur at the endpoints. Where this one, this function here, once again it's continuous, but now the global max is going to occur. So this would be like my C and my D if I was thinking about this. This would be my C, there's my min, my global min, where this guy right here would be my max, and then all the rest of them, you can see here, f of x is going to fall between. I know this just looks horrible. F of x is going to fall between. So you cannot, if you just draw a continuous function, you'll be able to see that in fact it must occur at a local max or local min. In this case, the derivative is zero. We're increasing and then we're decreasing. Okay, so we've got our conditions to be a local max. Okay, and the same thing, we've got our conditions to be a local min. All right. Now let's look at some examples. So I assigned a bunch of these up here. Okay, now I'm going to look at exercise 16 in the same set. Okay, and what's asking for is find the global max, find the global min of this function on that closed interval. So this is my A, and this is my B. Again, wake up. Okay, so let's do this. Let's try to find this. Well, it's not hard. The endpoints aren't bad. Okay, we can just say, okay, these are possibilities. F of 0 might be. We don't know. We're not plotting anything. We don't know. F of 0 might be a global max or a global min. Okay, so, and then we've got f of 4. F of 4 might be the global max or global min. So these are two possibilities that we got to put into the octagon, okay, to see who's gonna win. Now let's go looking for local maxes and local mins. Okay, how do we find local maxes and local mins? Well, we want to create and hopefully somebody said, let me see here, I'm trying to remember, Jordan, okay? Jordan, what do you think? What do we want to create for this function if we're looking for local maxes and local mins? And Jordan, are you saying anything? Did you say sign chart for the first derivative? You're exactly right. We want to create a sign chart for the first derivative because we want to find when it's increasing, when it's decreasing. And that tells us about local maxes and local mins. Well, to create our sign chart, we want our critical points. That's step one. Find the critical points of the function. Okay, but to do that, we got to take the derivative. Now, Diera, what's the derivative of this? What's the derivative of this? And hopefully, like Dr. Warren, I own this. This is 2x minus 2. Okay, so the derivative isn't so bad here. There's no way the domain is fine. There's no way for the derivative not to exist. So my critical points are only going to occur when this first derivative is 0. But that's the same thing as saying when 2x minus 2 is 0. And that's the same thing as saying 2 times x minus 1 is 0. And the only time that's going to occur, the only real number that's going to make the derivative 0, my only critical point is 1. Okay, so now I'm going to use that information. Now, with this sign chart, because we're looking for global maxes and global mins, I typically put my endpoints on here too. But because I'm ADD, I'll forget why they're there, so I'll put an E up here, because that reminds me, oh, those are endpoints. Now my critical point does fall between 0 and 4, so I'll put that in there. There's 1. Okay, the next thing I want to do is create my sign chart for my first derivative. Now again, I'm only concerned about the sign. Is it positive or negative? So I'm just going to pick one value between 1 and 4. How about 3? Okay, and I'm going to plug it in here. Well, if 3 times 2 is positive, that's 6 minus 2, which is 4. It's positive. So then everybody is positive in there, because because the function's continuous, if it ever went negative, we would have another 0, but algebraically this is my only 0. Okay, so everybody's positive in there. Now let's try a value in between 0 and 1, like 1/2. I put a 1/2 into my derivative, I get 2 times 1/2, which is 1, minus 2, which is negative. And the first derivative is going to be negative for everybody in between 0 and 1, again, because we can't have any other zeros. Now, this would mean I'm decreasing. They didn't ask this, but that would mean I'm decreasing on the closed interval 0 to 1. And I'm increasing on the closed interval 1 to 4, which would make, by definition, f of 1 a local max. That would make f of 1 a local max. Now there's no place on the interval 0 to 4 where I'm going up and then I'm going back down. Gosh, I'm a moron. Like Dr. Warren, you're going down, damn it, and then you're going back up. It's not a local max. That's a local min. Now there's no place where we're going up and then we're going back down. So we don't have any local maxes. So as far as local maxes, none. Okay. Now I want to point out something here, because I don't think you're going to appreciate it. How many points are there between 0 and 4? And if you go 1, 2, 3, okay, no. Okay, there's infinitely many points. Let's not forget our fractions. Okay, there's infinitely many points between 0 and 4. Are you going to arbitrarily guess the right one? That's going to be the max and the min. Where now, by the theorem that we have here, we only have 3 things we need to check. Okay, we're going to put this guy in the octagon. We're going to put this guy in the octagon. You're like, Dr. Warren, why are we talking about extreme fighting? Why are we talking about extreme fighting? And we're going to put this guy in the octagon. Okay, and the biggest of all those has to be my global max, and the smallest of all those has to be my global min. Now these do not, Dr. Warren, stop yelling at me. Okay? These do not go back into the derivative. We use our derivative to set up our sign chart, but when we're looking for global maxes, local maxes, we're using the original function itself. Say that. Now say it again. We're using the original function itself. Okay? So if I'm looking at the octagon here, we're looking at f of 0 because it's an endpoint. But when I plug 0 into my function, I get 0 squared minus 2 times 0, that's not 20, minus 3. You do the math right, and you get negative 3. So there's one possibility. Now let's look at the other endpoint, f of 4. I'll never be able to do this, Dr. Warren. Yes, you can. 4 squared minus 2 times 4 minus 3. Well, that's 16 minus 8, which is 8, minus 3, which is 5. Okay, so now if I'm looking there, I've got this guy as being 5, this guy as being negative 3. Right now, 5's winning for being the global max. Also, because there's no local maxes, this theorem guarantees that, in fact, f of 4 equals 5 has to be the global max. Now let's look for local mins, because that's where another possibility of getting my global min could be. Well, again, I plug it into the original function, not the derivative. Say that again. So I get 1 squared minus 2 times 1 minus 3. Okay, which is 1 minus 2 minus 3. You do the arithmetic correctly, you get negative 4. You get negative 4. Okay, so my global max is 5. You're like, Dr. Warren, do you say the 4? I typically don't, because sometimes 2 values give you that. But if you want, you can say it's 5, and it occurs in the domain when you plug in 4. My global min is negative 4. My global min is negative 4. And this occurs at f of 1. But if this is like, if we're thinking of like graphing this, we're not going to. If x has units of cows, and f of x, the range axis, has units of dollars, what we're talking about here is this is $5. It's related to the range. So the max would be $5 on the interval 0 to 4, and we'd be owing $4 as far as our global min. Okay, so this is the way, this is the process for a very simple kind of problem where we're looking for trying to find global maxes and global mins. Okay, so now you guys can pause this, write it all down, and then we're going to look at a couple more examples. And I'll look at the clock there. My board's getting filthy and squeaky. Like I said, that problem was pretty simple. That problem was that derivative was pretty easy to analyze. What if it gets a little more complicated? Okay, so let's look at another example. And if you're trying to follow, this is exercise 20. Sorry. On minus 3 to 1. That looks like a B, but it's a minus 3 to 1. Okay, so we're going to try to, again, find the global max and global min. Well, this one's a little bit harder to plot. The last one was a parabola. This one's going to be a little bit harder to try to analyze. But again, because of that major theorem, we know that the global max and global min must occur at a local max, did you say? A local min, very good, or the two endpoints. So we know 2 possibilities for our Usain Bolt and our biggest loser, the Dr. Warren, would be these 2 guys. Okay, so those are 2 possibilities. Okay, so now I don't want to look at all the numbers, all infinitely many numbers between -3 and 1. So now I want to use calculus, and I just want to go find my local maxes and local mins. And the way that we do that is create a, again, did I ask Jordan this? Jordan, what do? We create a sign chart for our first derivative. Okay, so let's do that. Let's take the first derivative. So you go ahead and do that. You go ahead and do that. So Julia, what do you get when you take the derivative of this? And hopefully, like Dr. Warren, I own this. We take that guy down, subtract 1. We take this guy, subtract 1, and the derivative of a constant is 0. So this is my derivative, and I'm going to create a sign chart for it. First thing I want to do is talk about the domain. No division, no square roots, no problem. Okay, we've got continuity with us. Okay, next, factor this. So go ahead, factor that. What can you factor out of each one of those? And hopefully you're like, well, Dr. Warren, I see a 3 in each of those. And then this has 2 x's, and this has 1, so I can remove that. So if you factor that out, what do you have left here? What times 3x would give you 3x squared? And what times 3x would give you 6x? And so we're here. Again, I don't have to worry about critical points where that doesn't exist. The derivative doesn't exist. This is a continuous function in itself. So now I just set this derivative equal to 0 to find my critical points in its factored form. And I ask, what are the real numbers? Algebraically, what are the only real numbers that would make this 0? Well, one would be -2. This one is one that students miss a little bit. 3 can't be 0, but x could be 0. So these are my 2 critical points. They didn't ask us what are the critical points, but those are your 2 critical points. Now we're ready to make our sign chart for our derivative. So we're here. Again, they're asking for global maxes and global mins, so I like to put my intervals on here. -3 is one of the ends. So I know I don't need to worry about what's heading over here. 1's the other end. And we can see that my true critical points fall in between these. It doesn't always happen that way. So -2 is one of my critical points that make my derivative 0, and 0 is another place that make my derivative 0. Okay, so now what I have to do is, those are the only zeros, is just test 1 point in each region. So I'm going to pick a number between 0 and 1. I'm like, great. Okay, how about 1/2? And I'm just going to look at the factored form of the derivative. It's easier in the fact. And all I'm caring about, positive or negative. Say that. Say it again. Positive. Okay, I can tell you're not focused. I can tell you're not focused. I don't know the song at all, so, but that is about how well I dance. I sit during all weddings. Okay, so then now we're down here. Pick a number between -2 and 0. And like, well, Dr. Warren, at least there's an integer. Let's pick -1. Okay, 3 times -1, positive or negative, positive or negative. And don't be like negative. -1 plus 2, positive or negative, and hopefully you said positive. Okay, and we got a negative times a positive, which is a negative. This is a little bit more yucky. We could pick -3 itself because we're only interested in the sign here. Okay, we don't have to go necessarily in between here because these aren't critical points. So if I just pick -3, I'm going to get a negative. I'm going to get a negative. Oh my gosh, I can't believe my phone while I'm videoing is, okay, well hopefully that will, sorry. Okay, so where we were here. We have a negative times a negative, which hopefully you said is a positive, Okay, now you write down what that means. What follows What follows from this? If you have that sign chart, what must follow? Okay, what does that mean about the function itself? And hopefully you're like, Dr. Warren, I'm drawing arrows. I'm drawing arrows, man. That means I'm increasing. The derivative is positive. We have a theorem that says it's increasing on the interval -3 to 2, decreasing in between -2 and 0, and increasing in between 0 and 1. Now again, they didn't ask for intervals of increase, but imagine that I did. Imagine that I asked for, like on a test, what are the intervals of increase? What are the intervals of increase? Well, it would be from -3 to -2, and between 0 and 1. If I'm only worried about this domain. If I was worried about the entire function, it would be from -infinity to -2 and from 0 to 1. Now I can put these together. I get out my welding mask and I weld that together with a union. Okay, so that, but again, they didn't ask for that. Okay, they asked for global maxes and global mins. So now I'm looking for what would be, where might a local max occur? Look at that increasing and decreasing. Where might a local max occur? Well, my local max, up, down. F of -2 would be a local max. Down, up. And these are my only local maxes and local mins. Okay, so now I'm ready to go hunt down my global maxes and global mins, because now I don't have to look at all the numbers in between -3 and 1. I just have to look at 4 numbers. I just have to look at f of 1, okay, f of -3, f of 0, and f of -2. So now I've got to plug all the numbers in, so let's just do that. Now again, do I plug them into the derivative, or do I plug them into the original function? I wasn't focused, Dr. Warren. Do you plug them into the derivative, or do you plug them into the original function? Do you plug them into the derivative, or do you plug them, you're scaring me, Dr. Warren, or into the original function? And you said, into the original function. So we plug them into the original function, and we get 1 cubed plus 3 times 1 squared minus 1. 1 plus 3 is 4, minus 1 is 3. Now, -3, this messes students up. It's -3 parentheses cubed. It's -3 cubed plus 3 times -3 squared minus 1. But -3 times -3 times -3 is -27. -3 times -3 is +9. Times 3 is 27. -27 and 27, they kill each other, and we're left with -1. Now we look at f of 0. We plug that in, and that's easy. That we just get 1. And now we've got one more f of -2. -2 cubed plus 3 times -2 squared minus 1. I'll do this one out. -8. -2 times -2 times -2. 3 times 4 minus 1. We get 12 minus 8 minus 1, which is 3. Okay. Now you look at our values. These guys were thrown into the octagon. Who's the global max? Who's the global max? And you're like, well, Dr. Warren, I don't know. F of -2 is 3, and F of 1 is 3. Who's the global max? The global max is 3. That is the global max. It occurs at 2 values, f of 1 and f of -2. But the global max is 3. The global max is 3. Like, for example, if x represented cats and this represented dogs, okay, what's coming out of the function represents cats, my range axis represents dogs, then we're talking about 3 dogs here, guys. That's what we're talking about, okay? We're talking about the dogs. Okay, so there's another example. There's another example. Okay, you probably need a drink. I know I do. It's just water, just water. No, it doesn't burn, it doesn't burn. Okay, now, let's look at one more example here. Can't believe my phone went off. Somebody's calling me.
8:00 p.m.
Oh gosh. That's my free app on my iPad that I have as a clock, as I have on a clock behind the wall here. Let me just give you a little spot of the room here. There we go. Do you see that? Okay, there. And then this is the rest of the paradise up here that I'm sure you've been missing. Like Dr. Warren, show us more of this place, this palace. Okay, so let's look at one more example. Let's look at one more example. One that's maybe a bit more beastie. Let's look at exercise 36, where we have f of x is equal to 1 over, fraction, Dr. Warren. Okay, so again, the question is to be or not to be. Okay, that is not the question. It's to be a global max or not to be a global max. To be a global min or not to be a global min. Okay, so now I want to try to find the global maxes and global mins on here. Now I got to be a little bit careful because now we got a fraction and we've got a denominator. Okay? But if you remember your quadratic formula, please, Dr. Warren, don't write down the quadratic formula. Guess what I'm doing. This gives me the roots of any quadratic. And I'm just worried, when is this 0? Well, if I look at the thing under the square root, if what's under the square root is negative, I know I know that there's going to be no zeros. If it's positive, I know that we're going to have 2 zeros, okay? And if it's 0, I know we're going to have 1 0. It's called the discriminant, not because it discriminates, but it's called the discriminant because well, I guess it does kind of discriminate. It discriminates between, is there 0 real solutions, is there 1 real solution, or are there 2 real solutions? But if I look in this case right here, my b is 2, so we'd have that b squared minus 4ac, which is 2 squared, minus 4 times 1, that's my a, times c, which is my 5, which is 4 minus 20, which ain't positive. So this is negative, which means this is never going to be 0, which for us is awesome, because it means we don't have to worry about the domain at all. Okay, so now this can't be 0, so now I want to try to find my global maxes and global mins. Well, once again, they could occur at the endpoints. So I've got to consider f of negative 2, and I've got to consider f of 1. I've got to consider either of those guys when I'm looking at the end. Now I want to look for local maxes and local mins. What's step 1? What's step 1? What's step 1? Hopefully you said take the derivative. So go ahead, you do the work for me. I would recommend quotient rule. I'm going to sit right here. Go ahead, take the derivative. You take the derivative. See what you get. Just pause it. Now I'm going to take the derivative. Now I'm going to take the derivative. Okay, so it'd be the derivative of the numerator, which is 0, okay, times the denominator, minus the numerator, which is just 1, times the derivative of the denominator, which is 2x 2x plus 2 all over the denominator squared. And this is nice. This is really nice. I love the fact that it's squared in this when we're analyzing intervals of increase and other things, because that means the denominator here is always positive. The denominator is always positive, and that's the way it is whenever we're taking the derivative of a fraction. That denominator is always positive and barely comes into play at all when you're looking at intervals of increases and decreases in sign charts for your derivative. Now let's clean up the numerator. These guys, that's 0 times any real number, 0, and then we're going to get minus 1 times 2x plus 2 all over that. Okay, now I can also factor out a 2. It's probably worth doing. Then I would get minus 2 times x plus 1 all over that denominator that's always positive. Next, people panic. People panic way too much when they hit fractions. They're like, oh my gosh, I'm never going to be able to do this. It's a fraction. But remember, you're looking for places. There's no places where the derivative is not going to exist because this denominator can never end up being 0. So I don't need to worry about that. And even if it could be 0, they wouldn't be in the domain, so I wouldn't even need to worry about them for critical points there either. But I'm looking for critical points. I want to find places where the derivative is equal to 0. With fractions, it's not bad, guys, because if you have a fraction of two real numbers and it's 0, the denominator is not allowed to be 0. Remember, we showed that if you divide by 0, all real numbers are 0. So this is not 0. The only way that you can get a fraction to be 0, because a over b by definition is a times 1 over b, is if a is 0. So when you're doing analysis for finding when the derivative is 0 and it's a fraction, you only need to be concerned as far as finding critical points where the numerator is equal to 0. So I just set this numerator equal to 0, which is like saying negative 2 times x plus 1 is 0. Negative 2 ain't 0, okay? The only value of x that's going to make that numerator 0 is negative 1. So at negative 1, the numerator is 0, denominator is not 0, the thing's 0. This is the only critical point. This is my only critical point. So now I create my sign chart. Again, it's asking for global maxes and global mins, so I'll put the endpoints on here. That's an endpoint. There's my other endpoint, my A and my B. Now my critical point happens to fall in between these. Well, Dr. Warren, what if it didn't? Well, then it's super simple. The derivative is just going to be one sign. Okay? And that's going to determine, you're going to have endpoint maxes and endpoint mins. But that doesn't happen so much in these kind of calculus problems in a book. So there's my negative 1. I know it's the only place that makes my derivative 0. So now all I have to do is test. Let's pick a number between negative 1 and 1. How about 0? Now again, I'm only concerned about the sign. The denominator is positive. I mean, that dude is positive. Okay? Now if I put a 0 in for here, I get 1 times a negative, which is a negative, and a negative divided by a positive is a negative. So it's really not any harder. Now in between negative 2 and 1, but because this is just an endpoint, I could just use negative 2. I could use negative 3/2, but let's just use negative 2. If I put a negative 2 in here, I'm going to get negative 2 plus 1, which is negative, times a negative, which is positive, divided by a positive, which is a positive. Now what does that mean? Dr. What does what mean? What does it mean to say the derivative is positive? What does that tell me about the function on the interval negative 2 to 1? And hopefully you like Dr. Warren. That means you're increasing. Derivative is negative, decreasing. Okay, so how many local mins do I have? on the interval -2 to 1, how many local mins do I have? How many times was I going down and then started heading back up on -2 to 1? You're like, none. That doesn't happen. So as far as local mins, none. Which means the global mins is one of these two dudes. The global mins is one of these two dudes. Okay, my local max, well, I've got one value up of -1. Okay, so I've gone from infinitely many numbers in between this -2 and 1, now down to just 3 that I need to analyze. So I throw these guys together. And it's a little bit more messy, but it's not that bad. Do I plug them into the derivative or do I plug them into the original function? And hopefully, like, I don't want to see you that close ever again, Dr. Warren. -2, remember, it's parentheses squared plus 2 times -2 plus 5. Well, that's +4, -4. They cancel each other. So we're just left with 1/5. 1, I like 1. 1's pretty easy. I don't even think I need to do much. 1 squared is 1. 2 times 1 is 2. And we get 1/8. I'm not even writing it down. There's 1/8. -1, I better be a little careful, being ADD. -1 squared plus 2 times -1 plus 5. Well, that's +1 when this is done. This is -2. This is 5. Okay, and what we get here is a 4 in the bottom. Okay, so we're looking at 1/5, 1/8, and 1/4. And what's the smallest number out of all of those? Well, it's this guy. If you have 1/8 of a pi, okay, you're getting gypped if you, in comparison to somebody who's getting 1/4 or 1/5 of a pi. All right, now my global max is going to be one of these other two people. My global max, okay, which amount of pi is more? 1/5 of a piece of pi or 1/4 of a pi? 1/5 of a pi or 1/4 of a pi? Okay, and hopefully like that's the, so my global max is 1/4. Okay, now, so the application problems, those application problems in the homework, you know, it's asking for the same thing. It's asking for maxes and mins. They've got applications that they've got, like, they're telling you what it means, but it's really no different. It's really no different. It's the same kind of strategy that you're using for this. Okay? Well, guys, thank you, and let me sign off here.